All right, let's dive into a really clever trick that teaches AI the difference between a pretty good answer and a great one. It's all about getting a machine to understand one of the most human things there is: similarity.
I mean, think about it. It really all boils down to this question. When you search for something, you don't just want a list of things that are kind of related. You want the best thing, right? The most relevant result. But how in the world do you teach a machine that kind of subtle difference? That's the real challenge here. Well, the secret, it turns out, is to actually make the training process harder. A lot harder. We're going to look at a method that forces the AI to learn the difference not just between right and wrong, but between right and almost right. And that's where the magic happens. So, let's start with the core problem. Human language is just messy, you know? To us, two totally different sentences can mean the exact same thing. But to a computer, they're just different strings of letters. The AI has to be taught all that nuance from scratch. Okay, look at this. You and I, we know instantly that these two phrases mean the same thing. No question. The goal is to get an AI to understand that too. And the way it does that is by turning these phrases into sets of numbers, called embeddings. We want the number versions of these two phrases to be almost identical.
So, where do you even start? Well, the simplest approach is to just show the model a correct match and then a completely wrong one. You can think of it as learning with total opposites. It's a decent first step, I guess, but it has one really big flaw.
This basic method is called training with an easy negative. You give the AI a correct pair, say a question and its answer. And then you show it that same question, but this time paired with some totally random, unrelated sentence from a book. It's a super simple contrast. This one fits, this one definitely does not. And right there, that's the problem. The model gets really good, really fast, at telling the difference between a correct answer and just random garbage. But that's way too easy. It's like learning to identify a cat by comparing it to a fire truck. Sure, you'll get it right, but the task isn't challenging enough to teach you the subtle details that separate a great answer from one that's just kind of in the ballpark.
And this is where a much, much smarter technique comes into play. It's kind of the hero of our story today. It's called multiple negatives ranking loss, or MNR loss for short. And this is where the real learning, the deep learning, begins. So instead of using random, unrelated junk as the negative examples, MNR loss does something way more clever. It takes a whole big batch of correct pairs, and it pits them against each other. Let me show you how that works. First thing, you just need a whole lot of what we call positive pairs. These are simply two pieces of text that you absolutely know belong together. The source material uses a perfect example, a big collection of research papers. Each paper's title is paired with its own abstract. That's a guaranteed 100% correct match. Okay, so we've got our big batch of correct pairs. Now for the really clever part, how we turn them into this powerful training exercise using something called in-batch negatives. So here's how it works. Imagine you've got a batch of, say, 64 of these title and abstract pairs. We take the very first title and we ask the model, okay, out of these 64 different abstracts, which one is your perfect match? The model's only job is to score its true partner abstract number 1 higher than all the other 63 abstracts. And those other 63, those are its in-batch negatives. See, they aren't random nonsense. They're all real, valid, plausible-sounding abstracts, which makes the task so much harder. And this right here illustrates the difference perfectly. On the left, you've got that easy negative. The sentences are about totally different things. No sweat. But look at the right. That's a hard negative. The question is about Amsterdam's population. The hard negative is also about population. It even mentions Amsterdam, and it has numbers. It's super related, but it's the wrong answer. Forcing the model to figure out the difference between the right answer and this very tricky wrong answer is what builds that deep, nuanced understanding. So the big question is, does all this extra effort actually pay off? I mean, we've made the training task way, way harder. Does that really make the AI perform better in the real world? And that's a fair question, right? The easy negative method is definitely faster and simpler. So is all this added complexity with MNR lost actually worth it? Well, let's take a look at the numbers. And yeah, the results are pretty clear. A model trained with a more traditional method, in this case softmax loss, it scores a 0.72 on a key performance test, which is okay. But that same model, when it's trained with this much more challenging MNR loss method, its score jumps all the way up to 0.80.
That is a huge leap in accuracy.
And that's really the heart of it. This is the key takeaway. It's not just about showing an AI what's right versus what's completely wrong. It's about forcing it to struggle with ambiguity. By challenging it with these hard, tricky, in-batch negatives, we basically force the model to pay attention to all those tiny, subtle details that truly define meaning and similarity.
Which kind of leads to a final thought, doesn't it? We've just seen that to make an AI smarter, you have to challenge it with difficult, nuanced problems. In education, this is sometimes called desirable difficulty. So if that's the key to making machines smarter, what do you think that says about the best way for us to learn and grow? Something to think about. Thanks for tuning in.